Today we move on to section 7.7 and we enter into the wonderful world of imaginary numbers. Imaginary student, what? Did you do this?
Well, yes.
Why?
I thought you made a mistake. Aren't you studying me?
No, I'm not studying you. We are studying imaginary numbers. Good grief. And you need to take some writing lessons. That handwriting is horrendous. No, we are studying imaginary numbers, not students. Not students. Section 7.7. All right, here's the deal. What is the square root of 25? It is 5. No problem. But what is the square root of negative 25?
Oh, isn't it just negative 5?
Well, I ask you this. Is negative 5 times negative 5 equal to negative 25?
No.
That's right. No, it's not. There's a problem here. Square root of negative 25 is not negative 5.
Oh, well then it must be positive 5.
No, because 5 squared is not negative 25.
Oh, I know. It's got to be 5 times negative 5.
Wait a minute. 5 times negative 5? That's not how square roots work. These numbers have to be the same. What number, when multiplied by itself, will give negative 25?
Well, I can't think of anything.
You know why you can't think of anything?
Why not?
Because there's no such number. In the real number world, there is no such thing as the square root of a negative. We've seen that before. But today we introduce the imaginary numbers.
Were they named after me?
No, they're not named after you. That's silly. Can't even think of a comeback for that one. Here's the deal. We define imaginary numbers like this. The square root of negative 1, which doesn't even exist in the real number world. It makes no sense at all. We call it I.
That's my first initial.
Yes, that is your initial. I. Square root of negative 1 is I. You might say, but what in the world is that? I don't know. It's that. But what's that? I don't know. It's imaginary. It's not real. It's imaginary. But at the same time that it's not real and it is imaginary, at the same time, don't make the mistake of thinking it's not real. It is real. It's just not real. It's not just imaginary, but it is imaginary. We define the square root of negative 1 as I.
Why would we do something silly like that?
Oh, there are lots of uses for this, especially in the world of fractals. It comes in handy. It's used in some physics applications with vectors, which we haven't talked about yet. Hopefully we'll get to that. It has some practical applications, even though it is just imaginary. Do not try to make sense of it. In a sense, it doesn't make sense, and that's okay. So, that is what imaginary numbers are. That leads to some interesting scenarios. Well, first of all, let's see what you're going to be doing with these to start with. Let's write a better name for the square root of negative 5. Isn't the square root of negative 5 the same thing as the square root of negative 1 times 5? Mm-hmm. And aren't we allowed to split that? We've seen that before. Doesn't that become the square root of negative 1 times the square root of 5? Yes. And don't we define the square root of negative 1 as I? Yes. So I change that square root of negative 1 into an I, and so the square root of negative 5 is I times the square root of positive 5. I call this, and sorry for the violence again, but I call this popping its eye out. Yes, we pop its eye out. That negative, it pa-chings. The negative goes pa-ching and turns into an I on the outside. We pop its eye out. I square root of 5. That gets a little more interesting perhaps with this guy. If I pop the I out, the negative sign pops out, becomes an I on the outside, but there's already a negative out there. Now please hear me on this. I is not negative. Sounds like poor grammar. I is not negative. I is not negative. I is the square root of negative 1. That's different. So the I pops out. Pa-ching! I end up with negative. That survives. Negative I square root of 7. Meditate on that for a while. Oh, here's a simple example I didn't even put on the board. How about the square root of, say, negative 16? We pop its eye out. Pa-ching! And the square root of 16 is 4. So we have I times 4. But there's a long-standing tradition. We don't write it that way. We kind of treat I like a variable. What makes a variable a variable? A variable is a variable because a variable can vary. V-A-R-Y. A variable is called a variable because a variable can vary. It can change. Does I change? No. I is always the square root of negative 1. It doesn't change. Therefore, I is not a variable. I is a constant. I is a constant, like pi. Pi doesn't change. It looks like a variable. It looks like the Greek letter. It is the Greek letter, but it doesn't change. It's constant. Likewise, I does not change. It is constant. It's always equal to the square root of negative 1. So back here then, what was my point? I've forgotten my point now. This I acts like a variable. Would we write x times 4? No, we would write 4x. Same thing here. We don't write I times 4. That's mathematically immature. We write 4I. It looks like a variable, it acts like a variable, but it is not a variable. It does not vary. So we just pop out the negative sign, it becomes an I. Take the square root of 16, that's 4I. 4I, done. This guy. Pop the I out. Negative comes out, becomes an I. I've got I square root of 99. But guess what? We still have to simplify radicals just like we've always done. What perfect square goes into 99? Thing simple. Yeah, 9. 9 times 11. The 9 pops out, pa-ching, turns into a 3. So now I have 3I square root of what's stuck inside? The 11. So all the old rules still apply. The only thing so far that's new about this is when you've got a negative under a square root sign, that negative pa-chings out and turns into an I. That's it. Let's move on to the next concept here. Oh, this is fun. What's I to the first power? Pretty clearly it's just I, okay, obviously. Okay, get rid of that. But what's I squared? Isn't I squared going to be I times I? And by definition, isn't that the square root of negative 1 times the square root of negative 1? But shouldn't the square root of negative 1 times the square root of negative 1 be equal to negative 1? Yes, it is. I squared is negative 1. But that's not possible. Ah, yes, in the world of imaginary numbers, it is possible. I can condense this. I squared, therefore, must be equal to negative 1. Notice how we're able to square. Remember, in the real number world, you square something, it's always going to be positive. But with imaginary numbers, if you square I, instead of being positive, it's negative. That's one of the most wondrous things about imaginary numbers. That's the weird thing about them. That's what makes them what they are. You square I, you get -1. That's a pretty cool concept. But how could that be? I don't know how it can be. They're imaginary. Don't try to make sense of it. Just accept it by definition. Definitions don't have to make logical sense to our meager human brains. It's just the definition. Well, that being the case then, what's I to the third? Isn't I to the third I squared times I? Well, of course. And isn't I squared just -1? So this becomes -1 times I. Well, -1 times I is better written as -I. So I to the third becomes -I. Let's condense that down and write it very simply, like this. Oop, left my dot behind. Grab that dot. There. I to the third is -I. Yeah, I know my eyes kind of look like backward J's. I always curl my eyes, and sometimes I curl them too much. Now let's consider what happens with I to the fourth. Isn't I to the fourth just the same thing as I squared times I squared? And doesn't that have to be, I squared by definition is -1. That would be -1 times -1, which is +1. Oh, fascinating. I to the fourth is 1. Because I to the fourth is -1 times -1. It's 1. Let's condense that sum here. Grab my 1. I to the fourth is 1. Now what's I to the fifth? Well, I to the fifth is clearly going to be I to the fourth times another I. But what's I to the fourth? I to the fourth is 1. 1 times I, which is just I. Do you see something cool going on here? Let's condense that. Grab my I. I'm back where I'm back where I started. So I to the fifth is also I, just like I to the first. Well, guess what I to the sixth is going to be? I to the sixth is going to be I times another I. I times I, -1. I to the seventh is going to be I to the sixth times another I. That's -1 times another I. That's going to be -I. I to the eighth is going to be I to the fourth times I to the fourth. That's going to be 1 times 1, which is 1. Can you guess what I to the ninth is going to be? It's going to be I to the eighth times 1 more I. Do you see the pattern yet? It's a pretty cool pattern. I to the first is I, then -1, then -I, then 1. Then I, -1, -I, and 1. Then I, then -1, then -I, I can do this, -I, and 1. Notice something special about these exponents across here. 4, 8, 12. Any exponents that are multiples of 4, it all cancels and you just get 1. 1. 1. So guess what I to the 16th is going to be? 1. I to the 20th? 1. I to the 100th? 1. That being the case, what is, not yet. Excuse me. What is I to the 101st?
Well, how do I know? Do I have to count all the way up?
No, because isn't that just I to the 100th times another I to the first? I to the 100th, all multiples of 4 just cancel out. It's equal to 1 times I, better known as just I. See, it becomes easy when you cancel out all multiples of 4 and then see what you're left with. So we could figure out I to the 1025th power. Now let's do 1026th power. Well, 1024 can be divided by 4. So we can throw out 1024 of these, and we're left with just 2 of them, which is negative 1. You can throw out any multiples of 4. Pretty cool. Yeah, I has some fascinating properties to it. Now let's do a little bit of arithmetic. Guess what 47I times 2 is? Well, the beauty of this is that I acts like a variable. 47I times 2 acts just like 47x times 2, which would be 94I. It's that easy. I acts like a variable, but it's not. Here, before you do any multiplication, you have to pop out the I. Pop its I out. So the negative sign pops out of the radical, becomes an I on the outside. We're left with the square root of 5 times 2I. But the cool thing now is, let's put these things together. I can multiply in any order, right? It's I times square root of 5 times 2 times I. It's all multiplication. I can do it in any order I want. So I'm going to put the 2 square root of 5 together first. 2 square root of 5. But then what's I times I? Is not I times I equal to negative 1? Get used to that. That's fundamental. You need to remember that. Because the square root of negative 1 times the square root of negative 1 is negative 1. So if that's all negative 1, that just makes this guy turn into, I need to make a little more space for myself here. Pull this over here. Because the I times the I becomes negative 1, that just makes the whole thing turn negative, so we get negative 2 square root of 5. How about this guy? Pop the i's out first. You must pop the i's out first or you will get the wrong answer. You must pop the i's out first. Don't forget that. I pop this I out and I pop that I out. What's that give me? Negative I square root of 3 times I square root of 7. Square root of 3 times square root of 7 is square root of 21. I times I is negative 1. Never forget that. That's fundamental. I squared. I times I, negative 1. But then we're taking the opposite of I times I. The opposite of negative 1. It becomes positive 1, which I don't even need to write down, and I'm done. Notice what's weird about this. Only possible in the world of imaginary numbers. I take something that looks negative, multiply by something that looks positive, and I get a positive. Only happens with imaginary numbers. Same thing with this next example here. This looks positive. This looks positive. We're going to multiply these two positives and watch what cool thing happens. 6 times 3, 18. I times I, negative 1. Yes, don't forget that fundamental concept. I times I is negative 1 because I squared is negative 1. Because the square root of negative 1 times the square root of negative 1 is negative 1. Meditate on that. Pause the recording if you have to and stare at that. So I times I is negative 1. That means we have 18 times negative 1, so our final result is negative 18. We take a positive number times a positive number, and because we're working with imaginaries, we get a negative answer. How bizarre is that? this example, pop its I out first. I square root of 3 times 3I. Well, put your 3 and your square root of 3 together. That's 3 square root of 3. But then I times I is negative 1. That makes the whole thing turn negative. Done. Done. By the way, what happens if you have something like, let's do real quickly here, square root of negative 9 times square root of negative 4. I pop the i's out. That gives me I square root of 9, which is 3. Call it 3i. Pop the I out. That's I square root of 4, otherwise known as 2I. That gives me 6I times I. But I squared is negative 1. My final answer is negative 6. Again, I took a positive times positive. It turns negative because I times I, like it or not, and believe it or not, is negative 1. It turns the whole thing negative. But what if I messed up? What if back here I said, oh, I know how to multiply radicals. You just multiply the inside, you get square root of positive 36, which is 6. Well, I'm afraid that's wrong. If you leave the negatives in there and multiply and then take the square root, you get the wrong answer. It's not 6. You have to pop the i's out first. Otherwise, you get the wrong answer. It should be negative 6 because of the I times I. That's critical. You have to pop the i's out before you multiply. Shall I say that again? You have to pop the i's out before you multiply. What do I have next here? Yes, okay. Let's scroll to the bottom of this blank screen here. Natural numbers. We're going to go back in time for a little bit here, back to pre-algebra perhaps. What are the natural numbers? The natural numbers are the numbers you naturally count with. What do you naturally count with? If I'm going to count all of the empty desks in this room, yeah, it's kind of sad, but I'm going to count the empty desks in this room. I don't start with a blank spot on the floor and say 0, 1, 2, 3. That's not natural. The first numbers that people came up with started with 1, not 0. 0 was a later invention. So the natural numbers are 1, 2, 3, 4. Sometimes we call them the counting numbers. They're the numbers you naturally count with. 1, 2, 3, 4. But what if we then add in the number 0 to this group? Now we have a new set that we have a special name for. Do you recall the name of the numbers where we take the natural numbers and throw 0 into it? Those are called, which sounds counterintuitive, but we call them the whole numbers. Throw 0 into the mix and now we call them whole numbers. So 0 is whole. Notice 1/2 is not whole. That's a fraction. It's not a whole number. Negative 3 is not whole. The natural numbers plus 0 make the whole numbers. Now if we take the whole numbers and we throw in the opposites of the whole numbers, so we throw in negative 1 and negative 2 and negative 3, no fractions. Just the whole numbers and their opposites. Then we get that group called, do you remember? Starts with I. We get the integers. Integers include no fractions. Of course, I've always got to be careful when I say that because, for instance, 10 over 5 is a fraction, but 10 over 5 is an integer. It's the number 2. So you understand what I mean when I say the integers include no fractions. But then what happens if I take the integers and I combine them with all the fractions between the integers? Then we end up with a group of numbers called rational numbers. I'm not going to elaborate much on that, but rational numbers are close to being everything. But then we got these weird numbers that you cannot express as fractions. We have this weird numbers like pi, like square root of 3, and many, many others. Numbers that cannot be expressed as fractions. Those are called irrational. They cannot be written as ratios. They cannot be written as fractions made up of two integers. They are irrational numbers. So if we take the rationals and the irrationals, put them together, we get that set that you've known about for a long time, known as the real numbers. Did you ever wonder why we call them real? There's a reason we call them real. Because there's another group that's not real. That's why we call them real. Well, I always wondered why we call them real numbers. I mean, like, aren't all numbers real? Then why do you call them real? That's silly. We call them real because there are numbers that are not real. The numbers that are not real are called, yes, imaginary numbers, such as square root of -1, which we refer to as I. Well, what happens if we take all of the real numbers, put them in the box, and take all the imaginary numbers, put them in the box, and mix them all together? Now we've got the combination of everything, real and non-real. By the way, sometimes we call these the non-real numbers. Put them all together, and we end up with another grand set that we call the complex numbers. We are now at the top of the number kingdom. I just made that up. I'm just on the spot. The number kingdom. I like that. We are now at the top of the number kingdom. Put it all together in one giant pot, and we have the complex numbers. So what does that mean? Everything is complex. 6 is complex. -3 is complex. 14/7 is complex. Pi is complex. Pi divided by 14.7 is complex. -32.5 is everything is complex. I is complex. Again, sounds like bad grammar. I is a complex person. I is complex. 5i is complex. 3 plus 5i is complex. What's complex? Everything. You used to think that everything was real. Now you know that everything is not real, but everything is complex. I always knew that math was complex. I always thought it was so complicated. How can I understand it? Yeah, you're telling me something I already knew, that math is complex. That doesn't mean it's complicated. We simply call them the complex numbers. If we looked at the Greek root of that word, it would probably make more sense, but it doesn't mean hard. It just means reals plus imaginaries. We call them complex. That's all it means. I took that chart, which was too big to fit in one screen, and I shrank it down so we can see it all in one place. It's kind of cool. Naturals plus 0 gives wholes. Wholes plus their opposites gives integers. Integers plus the fractions gives rationals. Rationals plus irrationals gives reals. Reals plus imaginaries gives complex. I like that. Isn't that nice? All right, we now move on. We have something called complex standard form. Any number can be written in complex standard form. Complex standard form looks like a plus bi, where a and b are real numbers, and I is the square root of -1. Examples: 3 plus 7i is already written here in complex standard form, where a is 3, b is 7. A is 3, b is 7. 3 plus 7i, a complex number. Can we write 5 in complex standard form? Yes. In complex standard form, 5 would be 5 plus 0i. It has no imaginary part, so it's just 5 plus 0i, where a is 5, b is 0. By the way, when I'm classifying these, I don't say that b is 0i. No, b is just 0. Like here, b was just 7. b is not 7i, b is just 7. How do I write, and we sometimes refer to this as a pure imaginary number because it has no real part. There is no a value. A pure imaginary number, 2i, how do we put it in complex standard form? It would be 0 plus 2i. The real part is 0, the imaginary part is 2i. A is 0, b is 2. 0 plus 2i. Notice anytime you have a number in the form of something plus 0i, it's going to be a real number. But if you have something in the form of 0 plus something I, it's going to be a pure imaginary. This guy is a mixture of the two. They're all complex. A little bit more arithmetic, and we're done. Guess what 7i plus 9i is? Again, I acts like a variable. So 7i plus 9i is just 16i. You're done. That's it. That's all there is to it.
But you said I times I was -1.
This doesn't say I times I. It's 7i plus 9i. We're not multiplying those i's. They don't turn into a -1. No, it's 7 of these guys plus 9 more of these weird guys. We get 16 of those strange guys. 16i. Same thing here. To add two complex numbers, add the imaginary parts and add the imaginary parts. Did I say the right? I think I said the wrong thing. Add the real parts and add the imaginary parts. You're done. Treat it just like as if it had said -5 plus 6x plus 2 minus 11x. It works the same way. It acts like a variable, but it's not a variable. -5 plus 2, -3. 6i plus -11i is minus 5i. We get the number -3 minus 5i, where a is -3, b is -5. It's now in complex standard form. Here, watch out with subtraction. I have caught some of you messing up on subtraction. What are we subtracting? We're subtracting the 4. We're also subtracting the 2i. So I have 2 minus 4 is -2. And I have 3i minus 2i. 3i minus 2i gives me 1i, better written as just plain I. And I have complex standard form. By the way, in this case, what is a? A is -2. And what's b? 0? No, it's not 0. What's in front of that I? The ever-present invisible 1. In this case, b is 1. A is -2, and b is the number that sits in front of the I that's normally invisible. It is 1. Oh, we're done. So your assignment, this is Wednesday, so this assignment will be due on Friday. Page 323, numbers 2 through 40 even. And please, some of you have not been properly formatting your subject lines, and it slows me down when I'm trying to quickly sort through my emails and get them all in the right folders. It's really, really easy if I can just see the Algebra 2A and Algebra 2B, then I just throw it into the right folder and I'm done with it. It's very simple. But when you do it backwards and I've got to be searching for this, or you forget to do this entirely, I have to slow down and remember, okay, what class is this person in? And it's a pain. So please, also for these guys, some of you are in physics, you're all in physics, so if you don't put this here, I'm not sure if it's physics or algebra, it slows me down. Please put the proper designation in your subject line and the page number so I can easily see what I'm looking at without having to go hunting. Stop making me hunt. I don't have time for hunting. I don't want to hunt anyway. Sorry, the point. Okay, we're done. See you next time.